So
can you make the oh, okay.
Yeah, I gave the wrong name though. It's called Peter Sharp's personal meeting room.
Can you not
unless
change
I
that?
stop it?
We
Let
can
me do it
rename it.
again.
Okay, just do it again quickly. I guess it'll only take a minute.
Okay, let me do it again. And it logs in from my account now automatically as well, which is great.
It does what?
Okay, what is this? What is the title of this again, please, quickly?
Peter, you are on the Access one, right?
Yes.
Okay. Neville?
yes.
Title.
What?
Well, what would your title be? Peter is asking.
Of what?
Your talk.
Oh, climate and its relationship with disease.
Climate and?
Its relationship with disease.
Okay, I hope I've got no typos. I'm going to rush this a bit. And we are live, everyone, in 3, 2, 1, 0.5.
Neville, do you want to stop sharing?
Yes. How do I do that? Stop sharing. I stopped.
It says preparing to live stream. Oh, we're only 5 minutes late. And can't upload it, right? My mistake.
No, I can see it. I can see it on YouTube.
Oh, are we there already? Because it still says preparing on my side.
Oh, something's happening. Yeah, no, it's live. It's up and running.
Fabulous. Then I guess over to Shivu.
Welcome everyone who's joining us live from all the other social media platforms. We are about to have a key lecture on climate and health given by the amazing Dr. Neville, who was, yes, Dr. Neville, who is going to give us a talk on climate and health. Dr. Neville is the director of Access and is actually a marine biologist and now is on health and climate. Dr. Neville, over to you.
Thank you very much. Thanks, everybody. Glad to be here back again with you all. Carl asked me to speak today, and I'm going to start with a disclaimer, which is a very bad thing to do. And that is to say, I'm not as prepared as I would like to have been, because I didn't have too much notice, but I've got quite a lot of stuff from previous talks and some stuff which we're currently doing, and I've lumped it all together and made some slides, and I'm just going to talk to them. And I would like it to be more of a conversation in the sense that there's lots of information I'm just going to talk to generally. And so I hope that you will just bear with me and we can engage with each other and just go along until I'm told to stop. I want to know whether you can see this screen where you can see some sine waves moving. Can you see that? Okay,
yes.
Good. So this is not news to some of you who have seen this 1,000 times before, but this is really where my research interest has sort of gone to, and where the program Access's research has gone to. And so I'm going to start with some basic concepts and principles and then take you into an application in the form of the kind of work that is being done, that we are doing, that I am doing and others are doing on the relationship between climate and health. But before we get to that, I just want to make this concept clear. We started a couple of years ago by looking at the climate question in a particular way. And that particular way is to look at the seasons. And I just want to spend a little bit of time talking about the seasons and why the seasons. So when we talk about climate change, and if I ask you to picture in your mind a graph that depicts climate change, what do you see? you can answer if you like. You just unmute yourself and talk. But I'm assuming what you're seeing is a hockey stick graph, the classic change of climate. But in fact, what you're looking at when you look at that graph is the average change of climate. You're seeing changes in temperature over time, or changes in some climatological parameter in time over years, right? But in fact, climate isn't like that. Climate is seasonal. And we have a climate change every year. We have a massive climate change in South Africa, probably less so in India, between winter and summer. We have seasons, okay? And so the annual average change tells us something, but not everything. And very importantly, especially in countries which have very high seasonality, and South Africa is one of those countries. We're in a very temperate region. We have very big differences between winter and summer. And so really what matters is how are winters changing over time and how are summers changing over time? That's really what matters. And so we started to look at this from a kind of a seasonal point of view, to ask those questions. Not so much how is the annual average changing, but how is summer changing? How is winter changing? And when we say that, we're asking how extreme are summers getting? So you might be asking how much hotter than normal or average is summer, or how much colder or warmer is winter than average. You also might ask, when is the beginning of summer and winter, or the rainy season? And is that shifting from week to week or month to month over time? How long are the seasons? When does the season start and finish? So there's a whole lot of parameters around seasonality. And this is the way in which climate change actually manifests in the changing seasons. That's really what matters to us, and I'll demonstrate to you why that matters. The annual average is important, but it doesn't tell us at the time and space scales that we really need to understand climate. So if you look at these graphs, this is an idealized version of climate, okay? The top panel, I don't know if you can see my mouse moving. The top panel is looking at what we call the thresholds of tolerance. It's the kind of summers or winters that we are used to in an ideal climate, right? And then I've got dotted lines, and basically we are all adapted to the summers and the winters that we already know. Some of us are less adapted than others. Poorer people, or people who have less resources, are less able to adapt to what we can call typical or normal seasonal extremes. So, you know, if you don't have the means to warm your house or to stay dry, etc., even what might be termed normal climate is difficult to adapt to. If you look at the middle one, that's to demonstrate something which we all know as extreme events, which happen all the time. With or without climate change, extreme events happen. We have an extra special storm of one form or another, or an extra special heat wave, or a drought, whatever that might be, okay? That's when occasionally a climate signal takes us beyond that normal threshold. And so we see damage to our environment, etc., etc. So the question about those extreme events is, are they happening more frequently? Are they happening more intensely? And are they lasting for longer? And that's another manifestation of climate change, right? And then the third panel at the bottom is talking about resilience. How is our adaptation? If we are becoming, for example, more densified as a population, and there are more informal settlements, is our ability to cope with extreme events or even normal climate change and variability, is that changing? So these are just concepts to kind of talk about the trends in climate, which manifest in the seasons. And I've got some examples of those in a moment, okay? I'll go to the next slide. I'll just put up these three images. So on the top panel of this slide, that's just to illustrate, for example, how in the first part, you've got what we might call typical or long-term typical climate. And then we might see an amplification of the seasonal signal. And that, if you take an average, means climate change as we traditionally know it. And the middle panel might be a trend, or there might be a combination of these things that all different patterns in which ways seasonality can change. So look, all I did was just to illustrate to you why, conceptually, why we want to interested in seasons rather than the long-term average, okay? And this is also illustrated here, and this is a nice paper. It's an Australian paper, which demonstrate this nicely. So there you can see a green line, and it's long-term climate variability. You can see the seasons in there. Note that it's a bumpy line, okay? And why is it a bumpy line? Because no one summer is the same as another summer. Every summer is different. We have interannual variability. Some of that, most of that is driven by natural processes. But there is a pattern, and we can see this pattern. So it's a bumpy line, okay? You see winter and summer. We also have, as I said to you, these extreme events. So we can call these pulses, okay? Every now and again, there's noise in the system. We have a big storm, or we have a long drought, which can be driven by various things. And then the third thing to talk about is the baseline change. And that's the blue line at the bottom. So you can see, and this is more traditional when we think about climate change, that the baseline is changing. If we combine these three lines together, what we get is something like this black line. This is what we experience. So you can still see the seasons, right? But the seasonal signal is trending over time, okay? And you can still see the extreme events. They're trending over time. They might be becoming more frequent. But what happens is those extreme events then push us up into areas where we've never been before. And those bands, the yellow band and the pink band, talk about survivable extremes and extinction extremes. This might be for a particular species, say, for example. When the extreme events take that trending annual cycle into levels of different environments that can damage the environment. So this is the concept of why seasons are important. Okay, I'll stop with that concept. Now I'm going to move on to another concept, and that is, how do we think about this in terms of disease? Okay, this is just one application. So I'm obviously going to talk more about South Africa. I've got very little on India, I'm afraid. But this is a map of South Africa on the right, and on the left are 8 different rainfall patterns, annual rainfall patterns. So we'll just take the top left-hand one, starts in January, ends in December, okay? And that's the top left-hand one, and let's compare that, okay? Sorry, let's take the one on the top right. You can see that in this picture, here we see January on the left, December on the right, and you can see the rainfall is most in the months of June, July, and August, 6, 7, and 8. Compare that to the one right at the bottom here, which is in the northeast of our country, and the one on the left of it's the same. Completely different rainfall pattern. January, February, March, most of the rainfall. In the middle of the year, hardly any rainfall, and then it picks up towards the end. So this describes our winter and our summer rainfall season. Remember that winter occurs in these months, ones we are in now. We are in midwinter, whereas in India, you're in midsummer, okay? And this image on the right really shows the start of the growing season. And the only thing I want you to show you here is that the start of the growing season, and again, this is the long-term average, is very different across South African continent, the Southern African continent. And that's because we have different climates, basically. So South Africa is very interesting because the seasonal pattern is very different in different parts of the country. So we have a nice little natural laboratory to study the seasons here because they are so different across the country. And we can look to see how these changes to the seasons happen in different climate zones. And similarly in India, India has a much more uniform climate, I believe, but you do have a range of seasonality in India, okay? India is much more tropical than South Africa is. And variability in climate is different in tropical zones. I'll get to that in a minute. Okay. So I was talking to you about extreme events, and what I wanted to say about those is that if you think about extreme events like floods and droughts, okay, but there are other kinds of extreme events like infestation of pests in crops or diseases like malaria, right? These things are all exaggerations of the seasonal cycles, right? We generally have a drought in the wet season, meaning it's normally raining in Cape Town in July. If it doesn't rain in Cape Town in July, then it's a drought, okay? The failure of the rains. But that's a seasonal effect. If it doesn't rain in Cape Town in January, well, that's normal, okay? So we can't have a drought in the dry season. We can only have a drought in the wet season, right? So where there's high seasonality and rains fail, then we have a drought. So that's an exaggeration of the seasonal signal, if you like. Similarly, you have flooding. In the bottom picture down there, if you can see it, is flooding in Johannesburg on the highways, right? Which happens periodically. And usually when you have extreme rainy season, then you get rainfall effects like an exaggeration of the rainy season. And this is true for many different extreme events like fires or whatever they might be. When they are unusual, it's usually an exaggeration of the seasonal signal. And similarly, there are diseases, which I'll talk to you about in a minute. There are diseases that are climate dependent, and they also they have variability and extreme events. I'm going to get to that in a minute. I wanted to say something. Of course, Indian climate is often driven by the monsoon. And when the monsoon fails, you don't get your rain, okay? And so that's important, but that's the season, okay? So if you, I'm talking about diseases now. So if I could tell you that I can predict the season, I can tell you that the next season is going to be wetter or drier or hotter or colder, and I can tell you what the relationship is with a particular disease, then I can warn you in advance of what's likely to happen with that particular disease. Take an example here of malaria. Normally, every year in South Africa, our colleagues who work in malaria management, they go out and spray in anticipation of the malaria season, but they don't know whether this is going to be a good year for malaria, as in not much malaria, or a bad year for malaria, lots of malaria. So they go out and spray all the time. And then when it starts to rain, they can say, oh, it's raining a lot. We better go out and spray again, okay? And we have to go and find people and money and so on and so forth. But if I could tell you, anticipate that this year, 6 months ahead of the time, this summer is going to be wetter than normal. They can prepare better. So if we understand the relationship between climate variability and a disease, we can then develop an early warning system. And that's really what we do. Okay. But to do that, we have to study the relationship between any particular disease and climate. Okay. So we've done that with malaria in South Africa. Incidentally, the leader of the laboratory we work with in Japan is Indian. There he is. He's a very good and close colleague and friend of mine, and his name is Sweijd Behera, but he lives in Japan. And in fact, our colleague from Durban is also of Indian origin. So just out of interest, but Sweijd is Indian, born in India, and he runs the applications lab in Jamstech in Japan. So we often talk about the delegation from Japan rather than the Japanese delegation, because they're not all Japanese. In fact, hardly any of them are. Anyway, we've looked at the relationship between some climate variables and the incidence of malaria in Southern Africa. This paper was published in Scientific Reports. And I also want to highlight a couple of things. Let's look at this. There's a top row and a middle row or bottom row. In the top row, that's at lag naught. In other words, it's the relationship between the climate at that particular time and the incidence of the disease. And then there's a lag of 3 months where we say, what was the climate like 3 months ago and what is the condition of the disease now? And all I want to do is highlight this bottom left panel. And this bottom left panel, you can see a red patch, and that's a positive correlation between rainfall in this part of Southern Africa, which is in Mozambique and in Zimbabwe, and the incidence of malaria 3 months later in South Africa. So when it rains in, say, September in Mozambique, above average rainfall in Mozambique, January, February, March. In March, we see a spike of malaria in South Africa, in Limpopo, in the north of the country over here. And why is that? Well, it's an indication that there's a reservoir of disease and of infected people who are coming into South Africa either for treatment or for work. There's migration of people, and they bring the disease with them, so they become the vectors. And there are other correlations, but this tells us that if we can watch malaria, rainfall in Mozambique, we can make predictions about malaria in South Africa. Okay. This is another one. I'll be very brief on this example. This just shows decadal change in malaria and why it's changed. So from 1998 to 2014, in a particular region of South Africa, and this is north is the long-term average. And we can see that from about 1998 to 2006, the incidence of malaria was above that long-term average. And then from about 2006 to 2014, it was below that long-term average. And why was that? We correlated this change with changes to sea surface temperature. So now we're looking at the sea surface temperature in the whole world, but we're focusing on the area where the rainfall comes from. And in these particular conditions, if they persist over time, for example, the ocean is warmer east of Madagascar and it's cooler south of Madagascar. In those conditions, we see an increase at the decadal scale in malaria because it brings more rain. And so if we can look at those patterns over time, we can start to make predictions. And these patterns are changing all the time, but at different time scales. So this is just to illustrate the relationship between some climate variability features and incidence of disease, okay? And this is an example of a prediction. This uses several climate models, and it's a probabilistic statistical model. I won't go into the details. And basically what it does is it takes a prediction for January, February, and March. That's what JFM stands for Limpopo, issued in December. And it takes the historical patterns and it says, well, based on those historical patterns, what do we predict going forward? And it can say, for example, in 2018, it says, well, there's about a 28% likelihood that we will have a below normal year. There is about a 15% likelihood that we're going to have an average year for malaria, but we have a 50 to 60%, like 58% likelihood that we're going to have a bad year for malaria. And then similarly for other years, it's very sensitive to El Nino. So that's the kind of information we can use. Those should total 100%, by the way. It's just splitting the probabilities. That's just an example. There are many other models that do the same thing. Okay, so that's malaria. Now I'm going to talk to you about my favorite subject, which is diarrhea. Okay, and diarrhea is a very important disease. I know a lot of people don't think so, but it kills more people, especially young people and old people, than any other disease. Perhaps tuberculosis and HIV are catching up, but as a symptomatic disease, this is the disease that kills more people. Okay. And one of the problems we've got is that the quality of the data we collect is very poor. And the reason for that is that diarrhea is not a notifiable disease. Malaria is, okay? But diarrhea is not. Cholera, which is a form of diarrhea, well, it's a disease that causes diarrhea, is a notifiable disease. But general diarrheal diseases, of which there are many causes, are not. And so we have very poor quality data. And so for us to look at that data is very difficult to see patterns. So I'm going to show you another kind of data, which we got. And what we did, and I don't know how this works in India, but in South Africa, you'll all be familiar with clicks, pharmacies, right? And I'm going to ask you to tell me, by putting up your hand, how many of you have had diarrhea in the last, say, 5 years? Okay, right? And I want to know how many of you took medication for it. Did you take any medication when you had diarrhea? Come on, don't be shy. I had it. I took medication. Okay. Yes, you took medication. And what medication did you take? Anyone? You can shout out. I want to know what medication you took when you had diarrhea. Are you all being shy, or are you all exceptions? Okay, I'm going to offer an answer since no one's volunteering one. You took Imodium. right? You all took Imodium. So it's the most commonly used self-medication. It's cheap. You can buy it over the counter. You don't need a doctor's prescription. So people buy Imodium. So if you look at the sales of Imodium, you can get a sense of how much diarrhea there is, okay? So that's what we did. So what you're looking at in the top left here are the number of, it's an index. It's the number of units of Imodium that are sold per week, which we aggregated per month over a period of time. And what you can see, these black bars, is it's very seasonal. Now there's diarrhea all year round, but it's usually in South Africa much worse in summer. Okay. And we want to understand, well, there's a relationship clearly with summer. So what's that relationship? So here on this bottom graph here, you can look at the climatology. Basically, there are 3 provinces given here. Okay, the blue is where I live near Cape Town. The red is Gauteng and the green is Limpopo, which is in the north of the country. Gauteng is where Johannesburg is. And you can see that the months of January, February, and March are all above average, the long-term average or the annual average, and December. But the other months are below average. Also, if you look, these lines are rainfall. And as I told you earlier, Cape Town has winter rainfall, and Gauteng and Limpopo have summer rainfall. So it's not rainfall that's explaining it, okay? It's not rainfall, it must be temperature. And we know this, we know that temperature drives diarrhea. But I just wanted to show you that to give you some more background information. Now here's something amazing. What we did was, we went and counted the times at which, so we know every summer, more Imodium is sold than in winter, right? But in some summers, a lot more is bought. There are extreme summers. So we took all of those extreme summers and we looked to see what was the sea surface temperature doing, right, when we had extreme summers, so extreme diarrhea. And what we found was this, and again, there are lags, right? I'll start at the bottom right at lag 0, lag 1 over here on the bottom left, top right lag 2, top left lag 3. And what you can see, these big red patches and blue patches, right? But at lag 0, which is the most significant one, you can see this big patch of red color over here, right? You see that? You see what I'm signaling? Big red patch of so that means that when the sea surface temperature in that region is warmer than normal, okay, then we see more people buying Imodium in Limpopo province in South Africa. I'll say that again. When the sea surface temperature in this region, which is off South America, right, Central and South America, and a bit off North America, when the sea surface temperature is warmer than normal, we tend to see more people buying Imodium in Limpopo. How in the world can that be related, right? I mean, I could go and look at the relationship between the price of bread in Uzbekistan and the sales of Imodium in Limpopo and find a result, okay? There must be a reason that links these two, right? Otherwise, they're just co-varying. And there is a reason. Can anybody guess what this is a feature of when the sea surface temperature is normally higher than normal in this part of the world? Does anyone know what that's called? Anyone? Except you, Carl? You're allowed to interrupt me. Okay, it's the El Nino. Okay? El Nino. And when there's an El Nino, it means generally in Southern Africa, it's drier and hotter than normal. Okay? When there's an El Nino, it's drier and hotter. So this is a signal of drier and hotter weather in Southern Africa. Okay? And that's the relationship that we are looking for. Is that a question that you have? Anyone? No? Yes? No? Okay. I won't go on about that, but basically the story, I'm just going to be very brief now because I want to get onto COVID and then I'm going to stop talking. But basically the story is that we find that temperature ultimately drives diarrhea. We know that. So different climate zones have different kinds of typical patterns of diarrhea. But we know that when it's drier than normal and hotter than normal, we get more diarrhea. Okay. So we can predict that. And when we predict that, then we can prepare for it. Okay. And in the long term, as climate change starts to bite, we can predict what kind of summers we're going to have in the future. What might that do to diarrhea, which is an important disease? Okay. I just want to draw your attention to this top right-hand graph over here. So at 0 on this graph, which is basically running along the middle of this graph, that's the long-term average monthly sales of Imodium. And so what I've done is for every month of the study, we've gone to see, did that month sell less than average or more than average, okay? And you can see in the middle is a big patch, which I've labeled B, okay? There's also a patch of positive that's labeled A, and one labeled C, and one labeled D. Now, the problem with this kind of data is that the data itself affects the average, but that's another discussion. All I want to point out is that there are 4 events of extra special diarrhea that we have identified. And B is interesting. We don't know what B is. We don't think it's got anything to do with climate. I think it's a novel virus that came around, just like an epidemic we're having now with COVID, and lasted for 2 years, winter and summer. But A, C, and D are very interesting, okay? A happened in the winter of 2010. Now, I want you all to think a little bit about the winter of 2010. Does anyone remember what happened in the winter of 2010? Shout out. Yes.
The FIFA World Cup.
Correct. The FIFA World Cup. We think that this was caused by the influx of people into the country bringing different bacteria and causing a spread of diarrhea. Very typical, okay? It's exactly what it was. But C and D are more interesting, okay? What is C and what is D? I'm going to get back to those in a moment. Am I? Yes, I am. Okay. So if you look at Cape Town, where I live, okay, you can see A, this is Cape Town. You can see B, it looks a bit different to the national picture. You can see C and you can see D. And if you compare that one, this one over here, with this one, there are some differences, okay? But I'll get back to those differences just now. But very importantly, C and D are very big in Cape Town, okay? I'm going to skip that one. Now, what I'm doing here is comparing them. So this is the graph I showed you earlier. There's A, there's B, there's C, there's D. Now, if you do that again for the whole country of South Africa, but you take out Cape Town or the Western Cape, and you do the same thing, you see a change. See, C is still there, right? But D looks very different. It's almost gone. There's a little bit of D, okay? That's comparing these two. C is still there, but so when you take Cape Town out, it doesn't make any difference to C. But if you take Cape Town out, it's almost gone. Okay, and this is another comparison of the two. And to cut the long story short, I'm going to explain to you that this event C, happened all over South Africa. All parts of South Africa had an extra special bad summer with diarrhea. And that was coinciding with the El Nino of 2015-16. There was a drought and it was much hotter than normal. And so that's why we saw more diarrhea. But the one at the end, D, happened much worse in the Western Cape than it did happen in the rest of the country. It was much worse of an outbreak. Okay, now the Indian colleagues will not know the answer to this question, but I'm hoping the South African colleagues will know the answer to this question. And the question is, what was happening in Cape Town in the summer of 2017-18? Can anyone remember? How short our memories are.
We had the water restrictions and the hectic drought.
Exactly. We had a massive drought. We are basically down to the last 10% of water in our reservoirs. And there were massive water restrictions. And people were, including me, showering as little as possible, no baths, were using shower water to flush their toilets, where sanitation levels plummeted, including in my house. And as a consequence of using less water, hygiene and sanitation levels dropped. We saw a spike in diarrhea as a consequence of that. The weather was fine. It was typical for summer. It wasn't hotter than normal, right? It was drought season anyway, because that's normally when it doesn't rain. So that's what. So now I hope I've illustrated to you this relationship between these various different elements, okay, of climate. And we looked at malaria, we've looked at diarrhea as examples. I'm going to finish with a consideration of COVID. Okay. So what do we know about COVID? We know that it started in China. All right, we think, okay? At least the outbreak started in China. It started in midwinter in China. It was December, November, December, midwinter of China in the north. And it started to spread into Europe during winter. It only started at the end of our summer, beginning of our winter in the southern hemisphere. Tropical areas, India got it earlier. But interestingly, it was very slow to take off in India. Very slow start. Then it started to take off, okay? Same with South Africa. Very slow, smoldering. Boom, then it took off. It coincided with our winter, right? So there are some patterns that suggest to us that there may be a climate driver, climate modulator. And there was hope and fear. Fear that in Southern Hemisphere countries, with the winter, I have left out a very important point, which I need to tell you this first. And that is that almost all respiratory viral diseases are seasonal, okay? Almost all. I'll get back to that just now. So the question is, if COVID is seasonal or is sensitive to environmental impacts, then if it comes to us just at the start of our winter, it's going to be much worse than it was where it started, because we're starting the winter with cases already, with community transfer into winter, and we expect it to be worse. It was also hoped that summer weather would dampen the epidemic in the north, which it hasn't, okay? America shows that very well. So the question is this or is this not related to climate? And I'll tell you the answer. The answer is, at this phase of the epidemic, it's not. There's too much virus. There is indeed evidence of sensitivity of this virus to environmental signals. And so it's likely that in the beginning phases, there was an influence of environment, which slowed its start or exacerbated it in various different parts of the world. But once it takes root and it's spreading, remember, you can get a cold in summer and winter, right? So just because there's more of it in winter, it makes it seasonal, doesn't mean it's exclusively a winter disease. So it can pass in summer. With so many people involved, the seasonal modulation is overwhelmed, and we can't see that signal. What's important is that there are 4 coronaviruses, human coronaviruses, which are endemic. They live inside humans, and those are seasonal. And so if this virus becomes an endemic virus, which is highly likely given its extent, that it will become seasonal over time, okay? That's likely. But right now, we can't see that signal, especially because it's confounded by lockdowns and by a whole lot of other factors. We can't separate out that signal. So our conference is addressing these questions, which I'm not going to talk about right now. I just wanted to show you this. I pulled out one thing from India. It's the bottom left over here off the internet. So most viral respiratory diseases are seasonal, even in the tropics, and sometimes associated with rainfall as opposed to temperature and humidity as it is in temperate climates. And sometimes in some countries you have different peaks, okay? This is fascinating. This is different years. So there's black is 2014, very low year. This is in India. This is of swine flu, by the way. 2015, when it peaked in January, and then later it came back, but later in the year, changing seasons. If you look over here on the top right, this is influenza in the United States. And you can see that in the weeks, this is week number, basically it's in a midwinter that the disease generally peaks, But the different one is this one, this gray one, which was 2009-10. There was a flu pandemic. It wasn't as serious as COVID, but it was aseasonal. And this proves the point that in a pandemic, the seasonal influence in initial phases is weak. And then finally, just I wanted to show you these two other panels here. If you look up at the top here, this is different months, January, February, right through to December, and it's where flu, influenza is prevalent. You can see, of course, there's much more land mass in the north, that influenza is very prevalent in January, February, March, April in the north, and then almost disappears and comes back in December. Whereas in the southern hemisphere, it starts in about April, May, right through to September. India, I looked at India, you'll see India, because it's tropical, has flu mostly in around March, April, and then it sort of disappears, comes back in June, July. So you have a kind of a bimodal pattern in India. And then finally, at the bottom right here is just the frequency of the disease in different countries. And the blue, for example, is the USA. And there you can see that at the beginning of the year, at the end of the year, which is the winter, whereas, for example, in Argentina, the peak's in the middle, much like in Africa, Southern Africa. Okay, that just shows you that these things are highly seasonal. And then I'm going to finish off by talking a little bit about the questions around COVID. So what is it in a disease like this that causes them to be seasonal? And if we understand that, we can start to look for those signals. Well, obviously, as we know, there are seasons for rainfall, there are seasons for temperature, there are seasons for humidity, right? Humidity changes. And this map on the left is just a map of the degree of seasonality. So you can see the Western Cape, we have very high rate of change of seasons. In this part, India, also fairly high rate of change of seasons, probably defined more by rainfall than by temperature. But the biggest seasonal changes are here in the temperate north, right? The east part of America, Central Asia, and Europe, okay? Be that as it may, that's one set of ideas that drive seasonality. The other is the human, is the host, right? And there are changes to us susceptibility. And very briefly, we just finished a review paper on this, so I'm sort of up to speed on this. Things that in the environment that affect the virus are things like UV. The more sunlight there is, or the more temperature there is, it kills the virus, it denatures the virus, right? And heat kills the virus. So the virus itself can't survive outside of the host. So that's a direct influence. In a human host, for example, things like vitamin D variability, which is generated from sunlight, okay, that ranges and changes with time, with season. So there's certain seasons when you have less immunity, or your immune system is not as strong. And so you're more vulnerable, you're more susceptible. So that changes seasonally. And there are effects of pollution that affect your ability of your throat, of your cilia to work effectively against particles. So there are all sorts of things that are varying in time with season. But the most commonly looked at item is the idea of droplet behavior. Okay, and this you might be familiar with. So I'm going to skip this one. But basically, there's a whole science of the behavior of droplets. And if I sneeze or I breathe or I talk, right, I'm producing droplets of saliva and of mucus all the time. All of us do it, okay? Even when we're talking, right? And they come out in different sizes. And the smaller the droplet is, the longer it persists, okay, in the floating around. It becomes aerosol. Or it settles onto a surface, okay? And inside these droplets sit our virus, and that's called a pathogen-bearing aerosol droplet, okay? And the fate of that droplet is determined often by environmental conditions. So, certain conditions allow that the virus inside the droplet to remain viable, to float for longer, to travel further. And if they land on a surface, it becomes called the fomite. This is now an infected surface. If the surface is cool and moist, it will survive. Okay. And so once we understand these relationships, we can start to manage the disease. For example, internal environments, we can decide what's the optimum humidity, which balances both comfort and preventing the disease from spreading too easily. And so all of the science is really focused on managing the transmission of the virus, basically the connection between the environment and the disease is through droplet management, okay? I'm going to finish by just saying that we're looking at the potential of the environment to affect this across South Africa, and this is just an example of a factor which we've worked out based on temperature and humidity and the climatology. You can see that the effect of these environmental parameters on the potential for transmission, not on the transmission, but on the potential for transmission, varies over time. This is what it looks like in March. This is what it looks like in June, because in June it's colder and it's drier. So the virus will survive longer. Okay. Final slide is to say that because of ranging seasonality, the environmental driver, such that it is in COVID, might vary in space with latitude. And so this chart basically tells you with and without humidity, what it looks like, this transmissibility factor, environmental factor across the world. And you can see it's effective, more effective in some areas than in others. Okay, I'm going to stop and finish by saying, I hope I've illustrated to you how we think about the changes to climate in the seasonal sense, why seasons are important. And an example of this is the application in health, where we're looking at diseases like malaria, diarrhea, and COVID, and how we can think about the relationship between climate and health and how this really matters and may matter in time. I'll stop there. Thanks.
Thank you so much, Dr. Neville, for the talk.
I can hear you very well.
Thank you so much, Dr. Neville, for the talk. May we please have a round of applause for Dr. Neville and then some questions. A round of applause. Thank you. Now, can you please have questions from the floor?
If there are any.
There are.
Hi, Neville. So I just have one question. With climate, or with like global warming, it's projected that temperatures will rise by like 1.5 degrees, but double that for Southern Africa. So does that mean if Southern Africa is significantly warmer, will we get more diarrhea and will it be more hectic? Yeah, so I was just wondering about that. How does the projected temperature increase affect the malaria and the rain and the diarrhea?
The question we have to ask is, which diseases are sensitive to temperature, right? We have to ask. We'll just pick on malaria for a bit. And this applies all over the world, not just in Southern Africa. But interestingly, malaria has a temperature window. There are certain temperatures above which it's not good for malaria, for the parasite, right? The parasite doesn't survive. And then there are areas where it's too cold. Okay. So if climate is warming, it is possible that in some areas, it will become too hot for malaria. And in areas where it was too cold, will become malaria areas. So we might see a shift to the distribution of a disease. Similarly with elevation, okay? The areas where it's higher, so it's cooler. And when that happens, we might see malaria going up rather than, so we might see a change in the demography of diseases. Then there's a question of the severity of the diseases. And again, there's a window of optimal, there's an optimal temperature. Also very importantly is diseases adapt, just like animals adapt, just like humans adapt, okay? So with new environmental drivers, so we might see changes to diseases. The best thing I can say is forearmed is forewarned. If we are able to make these predictions with some confidence, then we can manage that impact. That's what adaptation is about, okay? It means better sanitation, which should happen anyway, of course, but it means we can say, look, we expect 10% or 20%, we can model it. If temperatures go up by average of 1% in 10 years, we can expect a 10% increase in diarrhea in whatever particular area. So the answer is we will unquestionably see an effect, okay? But we can manage it.
Thank you, Helen, for the question, and Dr. Neville for the answer. Dr. Carl?
A follow-up on that, Neville. I don't know if you know where the biggest ever malaria outbreak was in the world.
I do not.
It was in Archangel in Russia, in the Arctic Circle, in freezing cold weather. So how do you, I don't understand, I genuinely don't understand this. This is a genuine question. Why are we postulating that there's minimum temperatures for malaria when the biggest outbreak ever was in the Arctic?
Funny thing that I saw a mosquito in my bedroom 2 nights ago in midwinter. I thought, now that is something I should really look into, right? Why is it that I have a mosquito at this stage? Carl, I don't know the answer to your question, and I'm interested to know what we mean by biggest outbreak, because, for example, I'll tell you a related story. There was a case of a man who presented at a hospital in France, which has no malaria, very ill with a fever. And they tried to diagnose this guy and they just could not diagnose him. And in the end, they found out that he had malaria in France, but there's no malaria in France. So how did they find out he had malaria? Well, they worked it out because he works in the airport. And what had happened was a mosquito had flown over in an aeroplane, and he kind of opened the door and the mosquito came and bit him on the nose. And the next thing, this poor guy had malaria in France, right? And so what happened was there was a 100% increase in the malaria cases in France from 0 to 1, okay? So when you say there was the biggest malaria outbreak in, where is it? In the north.
Yeah.
Yeah.
It was during the Second World War, so I guess it could have been brought in by the war. So we're talking 1940s, but it's the most death in one outbreak.
Yeah, I don't know how to answer that to you. The question is, did it persist? Was it a one-off event? You know, because we do get these outbreaks. One of the interesting phenomena in South Africa is we do a lot of malaria control, but despite that, every now and again we have a village where there's a boom, an outbreak, 100 cases, right? And this is very similar to what we're seeing in COVID, right? You get mass spreaders. So you have some poor soul who's been infected, but is actually asymptomatic because this person is immune, has this natural immunity. So they are carriers of the disease, right? They come to sit in the village, and then a local mosquito bites them, suddenly has the parasite, and suddenly there's a whole lot of people get sick, right? Can be one mosquito that makes 10 people sick. So the answer is I don't know.
Thank you for that. Do we have any other question? Yes, Tepi.
Oh, okay, Dr. Neville, thank you for the presentation. There's a slide that had a question that says, what sectors of economy does seasonality affect?
Yes.
Yes,
I didn't get into that. Yeah.
Yes, maybe please go to that slide, because I saw some graphs that I do not understand.
Okay, let me just get there. Hold on. Bear with me, and I will share my screen. Oh, I remember which one you're talking about. Yep. Okay, give me 1 second. I'm almost there. Yep. I think it was this one. I'm going to share my screen again. Share screen, and this. Okay, it was this. This is the one.
Yes, this is the one. I don't understand the graphs. Maybe if you can maybe explain.
Sure. It's a theoretical concept, really. Okay, but so all I'm saying is that if you take green to be the long-term average, okay, of let's say we're looking at temperature. Okay, this blue sine graph is temperature. So the long-term average is determined by the last 10, 20 years of average temperature, okay? And and we can see the oscillations between summer and winter and summer and winter. Now with change, we're seeing that the temperatures are getting much warmer in summer and much colder in winter, right?
Yes.
And if they increase as much as they decrease in winter, then the average will stay the same, okay? So the average doesn't really tell us much about what's changing on the extremes, right? I mean, the average is still the middle point. So the average of 1,000 and 1,000 and minus 1,000 is naught. The average of 100 and minus 100 is also naught, okay? So this is just saying that if the amplitude of summer and winter are changing, the annual average doesn't tell us a lot. Therefore, we must look at what's happening at the peak of summer. We must compare summers to summers to summers and winters to winters to winters, rather than annual averages 1 year to the next. That's one point. The middle panel is just saying that this is the same scenario, except here, the summers are getting warmer, but so are the winters. So the annual average is changing. Okay, the green line is trending up. And if we combine these, sometimes we get periods. For example, there's a purported 18-year signal in the rainfall in the Western Cape, that there are long waves. Sometimes we see the last 10 years have been warmer than the 10 years before those. But then we return back to the next 10 years. So this is just looking at different scenarios, different ways in which climate can trend, both between years, right? Between years and over 10 years and over 100 years. They can trend in all different ways. That was just to illustrate the theoretical idea. Okay.
Oh, okay.
Yeah, I didn't address the question of sectors of the economy, but that you can think about if you have some time.
Yes. Thank you.
Sure.
Thank you, Tepi, for that question. Do you have a question from India, perhaps? Sneha? Jijo? Yes, Sneha.
Yeah, hi. In the last slide, you told something about the seasonal cycle in TCCF and CCF. I couldn't get it, so can you please explain?
Yeah, I'm not going to, it's actually not my work, so I'm not going to be able to explain it very well to you, but I will just show it to you again. This is something which is in fact in press. Oops, just bear with me a second. It's in press right now, so I'm not really allowed to show much of it to you. Let me just go back to sharing my slides. This one over here. This one. Is that the right slide? Yeah, okay. So just look at the bottom one. So the climate correction factor is a factor which says by how much will transmission rate of COVID, right, be affected by climate. So let's just say, you know, and basically it's dependent on temperature and humidity. Okay, so we're saying, assuming that transmission is affected by climate, by temperature and humidity, we can make a calculation. We can develop a little mathematical tool that says by this much, and that's called the climate correction factor. So we have an infection rate of 0.6, we multiply it by this climate correction factor. That climate correction factor varies in its impact in different parts of the world, depending on what's typical climate. Okay, it will vary by month. And basically we can average that and say, well, on average, that climate correction factor's power to affect the infection rate, right, varies in different parts of the world. And where it's black, in black color here, of which I believe northern part of India is implicated, is where this climate correction factor's power is greater. And where it's light yellow, which is mostly in sort of Saharan, Central Africa, and some of the tropical regions, its effect is very low. Okay, so all this is saying is that if we can assume that there is an effect of humidity and temperature, right? We can assume that the power of that effect varies in space and across the world. The black areas where the power of this factor is greater and the light areas where the power of that factor is lower. Does that answer your question? Good.
Thank you, Sneha, for the question. Do you have any other question from the floor? Dr. Carl?
Last one. I've got to go.
Let Kayleen go then.
No. Ask the question, then I'll go.
Kayleen has a question, so rather answer that question than mine.
Okay.
Dr. Carl, you're muted.
I just want to say it was a brilliant presentation that I really enjoyed. It's not actually a question, but rather a comment. Something that I found very interesting in your presentation was that you used the purchasing of medical products to track the progression of a disease and relate it to temperature and seasonality. I thought that was like really interesting because I never thought of that before. I enjoyed it. I learned something new.
Good, thanks. It's a lot of times people use proxy data to get at something because the data you actually want, the thing you want to measure, you can't measure. So you have to find something which is a proxy for that. And that's what we've tried in this case. Thanks. All right.
Yes, Dr. Neville.
So guys, I have to leave you because I have to prepare for another meeting which starts at 3 o'clock and then another one starts at 4:30. So thanks very much and I will see you again.
Thank you. Thank you for sparing your time to be with us, Dr. Neville.
A great pleasure.
A round of applause for Dr. Neville as he leaves. Thank you and bye, Dr. Neville.
Thank you, Chivu. Thank you, everyone. We can go relax now. Another wonderful day, and let's hope to be on time again tomorrow. Oh, I'll leave the Zoom running. If anybody wants to hang around, you're welcome to. Just so it's there in case you need it.